Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about state functions and how that pertains to us calculating different heat values. We're going to talk about pressure volume work, which is the work involved in chemical reactions and how we measure them, as well as the idea of enthalpy or heat of reaction. So let's get into this video. So the first thing we're going to talk about is the idea of a state function. And when we're talking about this in general terms, we're going to talk about the beginning and the end of some operation. So the initial analogy I like to use is thinking about traveling to the District of Columbia or the United States Capitol. So you could be in your hometown, your home city, and we're going to need to get to the Capitol. So we could drive there and take the major interstate routes, or we could fly into Reagan National or Dulles International Airport. For Reagan National, we could just walk across the Potomac River. If we flew into Dulles International Airport, we're going to need to take the metro system, which is the train system. So we could take the Silver Line Metro into DC. You could fly the complete opposites around the opposite spin of the Earth, and we could go all the way around the Earth and land at Reagan National. We could have walked from our initial destination. So you have an infinite way to go from your town to the District of Columbia. But in order to see the total distance overall that you've gone is wherever you started and wherever you ended, that's all that's really going to matter. So when we're talking about state functions, this is the idea we have to use. So when we're talking about the internal energy of an object, so say something like room temperature water, the room temperature water may have been from boiling water to go to room temperature, could have been from ice to come up to room temperature. We could have went from ice to boiling back to room temperature, but all that matters is where you started and where you ended. So internal energy is an example of this. So the internal energy of a system is going to be final minus initial to calculate the overall internal energy. When we're talking about heat and work though, these are not state functions. They're going to vary. So say we had a charged up battery and we connected that to a resistor and we depleted the battery all by giving off heat energy. If we took that same charged battery and hooked it up to a fan, now the fan is moving, so there's some work being done, as well as heat is being lost by the mechanical pieces in the back and whatever resistors might be back there as well. So we're still going from charged battery to dead battery, but we've gotten there through a different method and our heat values and work values would have been different respectively. So that brings us to our next topic, or the idea of pressure volume work. So usually we measure the work of a reaction, a chemical reaction, in a closed system with a movable piston, and that's considered an open container where the atmospheric pressure is the pressure of the surroundings. So you're going to have some moving piston, and we could calculate the work, which is going to be equal to the negative pressure value, the constant atmospheric pressure, times the change in volume of the system. So now we have an idea of how we can calculate work for reactions using pressure volume work. We can start to derive enthalpy, which we consider equivalent to heat. So we're going to go through a mathematical derivation to see how enthalpy, or the change in enthalpy, is equal to the heat lost or gained by the system. So we're going to have to assume that we're at constant atmospheric pressure wherever room or place that you're in. The pressure is not fluctuating, and the only work that's done is pressure volume work. Well, then heat is going to be equal to enthalpy. The symbol we use for enthalpy, H, is equal to the internal energy plus pressure times volume. So if we were to find the change in enthalpy, delta H, that would be equal to delta of this other expression, E plus PV. I told you that we were going to be at constant pressure, so we can pull the P out of that PV term and pull it on the other side of the delta symbol. So now we're left with delta H equals delta E plus P delta V. If we remember from before, delta E is equal to Q plus W from the previous video. So change in internal energy is equal to heat plus work, and we could substitute that in for delta E. So instead of delta E, we're going to put Q plus W. A couple minutes ago, I just told you that work was equal to negative P delta V for our pressure volume work. So then we can just substitute our P delta V term for negative work. And now our works are going to cancel out, and we're going to be left with delta H is equal to Q, and this is going to be the enthalpy value is equivalent to heat at constant pressure. So now we can start talking about heat flow processes with regards to reactions. So if we calculate the enthalpy change of a reaction, we find that delta H is greater than 0. That means this is an endothermic reaction. Heat is going to be going into the system from the surroundings. The system has gained heat. If their delta H value is less than 0, this is exothermic, or the system is dissipating heat. So there's going to be a release of heat from the system to the surroundings. So we could calculate the delta H of a reaction, or delta S or delta G. They're all going to be the same. What you're going to do is you're going to take the sum of the delta H products minus the sum of the delta H reactants, and that will give you the delta H of your reaction. So you're going to have these tables in common textbooks called enthalpies of reaction table, usually in the back of the book. And for each different compound, you can just look up the delta H of formation right from that appendice. So there's going to be three things that we need to remember for enthalpy. The first thing is that enthalpy is extensive. And if you remember from one of the first videos, an extensive property means it depends on the amount. So if you got more stuff to release heat, the heat value is going to be bigger. So if you're thinking about candy bars and calorie content, one candy bar has 100 calories, well then 2 candy bars is going to be 200 calories. The second thing we need to keep in mind is that delta H is going to be some value in the forward direction for a reaction. It's going to be the equal and opposite sign in the reverse direction. So say we had some combustion reaction and we released 2,000 kilojoules of heat, so we've got a negative 2,000 kilojoules in the forward direction. To go backwards, we're going to need positive 2,000 kilojoules to go in the reverse direction. And then the third thing to remember when you go to look up those values in the table or appendices in the back of the book, delta H is going to depend on the phase that the compound is in. So there's going to be a different value when you're talking about solid, liquid, or gas phase. So just remember that when you're doing your calculation so you don't plug in a wrong number. So there it is, you guys. There's the video on state functions, the idea of pressure volume work, and the idea of enthalpy. So if you found this video useful, smash the like button, send it to your favorite sea creature, send it to your favorite world leader, and we'll see you in the next video.